Good evening, everyone, and welcome to the second Haag-Streit Academy Improving Outcomes webinar. This session will focus on some of the more advanced elements of biometry, including post-refractive surgery and toric IOL calculations. My name is Grant Duncan. I'm the Clinical Training Manager with Haag-Streit UK. I'm joined again this evening by David Sculfer and my colleague and Senior Product Manager for the Lenstar LS900 optical biometer, Sam Laidlaw. Thank you all for taking the time to join us this evening. Once again, although the majority of our attendees are based here in the UK, I'm excited to see we also have a significant number of international attendees joining us from as far afield as Portugal, Greece, Iraq, and Canada this evening. Many of you joined us for last week's basic biometry webinar, and some of you will also have attended one of our Improving Outcomes live training events in the past. I'm pleased to say that we're planning to begin running these again from summer next year. Today's webinar will feature some elements from these face-to-face courses and will again be presented by our key faculty member, Mr. David Sculfer. David is a consultant optometrist and head of optometry based at Stoke Mandeville Hospital in Buckinghamshire. His special interests include biometry, electrodiagnostics, and diabetic retinopathy screening. He is an expert user and key opinion leader in the UK for the Lenstar biometer. Once again, you'll be able to enter questions on the Q&A tab, and this will be monitored throughout the session by my colleague Sam. We will take some time to answer as many of these questions as we can at the end of the session, but if you have a question that we don't manage to cover, please email me at the address on the thank you email you should each receive tomorrow. We are again recording this webinar and will send you a link when it's available. So without further ado, I'd like to hand over to Mr. David Sculfer. Thank you.
Thank you, Grant. So tonight, as Grant said, I'm going to start with toric IOL planning. So why is toric IOL planning important? Well, there are unfortunately an awful lot of pitfalls in using toric lenses. We started using them in our NHS patients. We now do about 10% with a cut-off of an expected post-op astigmatism of 2 diopters. So anything above that is eligible for a toric implant. But we really had to change some of our procedures because preoperative measurements become much more critical, particularly keratometry. We had some problems initially because although we were taking into account posterior corneal astigmatism, trying to calculate surgically induced astigmatism for a bunch of surgeons, some of whom operate in one position, some in another, was really quite difficult. Getting the IOL in the right place was difficult because that relies on very accurate marking of the patient, which itself is not always easy. But every time you get an error of 10 degrees, you'll lose about 1/3 of the toric power. So by the time you get to a 30-degree error, you will effectively not have a toric correction at all. And if it's more than 30 degrees, then in fact the astigmatism will increase. But of course, this becomes more of an issue with the amount of toricity that you're trying to correct. So if you've got a high-powered toric lens, let's say an Alcon T9, if you get that one 5 degrees off axis, then that will have a big effect. If it's a T2 lens, 5 degrees will not be here or there. So it's important to note that you have to be more accurate with higher amounts of astigmatism. I'm going to first of all review keratometry and topography. This is, for those of you that were here last week, it's nice to see you back. For those of you that weren't, I made the point that keratometry and measuring the cornea is rapidly becoming the limiting factor in accuracy of biometry and IOL calculations. So keratometry is measurement of the curvature of the central 3 mm of the cornea. The exact amount differs between instruments, but generally it's around 3 mm. So we have no idea what's happening outside that central 3 mm area. We're also only measuring with conventional keratometry the anterior surface of the cornea, or in fact what we're measuring is the tear film, but we're not measuring the posterior curvature. So the keratometry reading gives you 2 meridians, the steepest and flattest. If it's regular astigmatism, then they will be 90 degrees apart. If it's irregular astigmatism, for example, in keratoconus or the scarred cornea, then those maximum and minimum meridia will be not at 90 degrees. And that's important to identify because those patients cannot be corrected with a toric implant or indeed with glasses. You would then be having to look at a contact lens, a rigid contact lens most likely. So it's important to identify irregular astigmatism because those patients are generally not suitable for a toric lens and certainly not suitable for a multifocal lens. So in keratometry, we can get two different units. We can either get the power in diopters or the radius of curvature in millimeters. And in fact, what happens is you actually measure radius of curvature and then you convert to diopters. And to do that, you use this thing called keratometry index to convert one to the other. Now, the keratometry index is related to the refractive index of the cornea, but it's not the same thing. And one of the problems is that it ranges around the world for quite different figures. So from 1.3315 to 1.3380, in the UK we usually have 1.3375. The difference between those is 0.8 of a diopter. So once you've measured the curvature, you then convert it into diopters. Depending where you are in the world, you come up with a 0.8 of a diopter difference. Now, in fact, that doesn't matter as long as you are consistent and all your instruments expect 1.3375 if that's what your instrument is calibrated to. It's a good idea just have in mind what an average cornea looks like. So an average corneal power will be 43.5 diopters. The reason that's useful is it then allows you to spot when you've got an unusual cornea, so it's unusually flat or unusually steep. An unusually flat cornea may have had refractive surgery. A steep cornea may have keratoconus or some other ectasia. So keratometry is traditionally measured with the Abulafia keratometry you see at the top there. We still have to resort to the manual keratometry occasionally because if you've got a very distorted cornea, you need to come up with some sort of figure. You can't do the calculations without putting in corneal power. And if you've got a very distorted cornea, sometimes the automated keratometers will either give you a hopelessly inaccurate reading or more likely won't give you a reading at all. At least with the Abulafia, looking down the telescope, you can get a position where you think the cornea looks of reasonable shape and you can get some sort of idea of the curvature. So we do still need that occasionally. But most of the time we're using an automated keratometer. They're either built into the biometer or they come as part of an autorefractor setup. So automated keratometry works by projecting images of lights onto the cornea and then photographing them. Now it makes the point there, actually what you're projecting it onto is the tear film, and as I said last week, that causes problems because if you've got a patient with dry eyes or an unstable tear film, every time they blink you will get a different reading. So you need to stabilise that tear film first. The original IOL master used just 6 peripheral points. The central one is simply a reflection of the fixation light. The IOL master 700 has 3 concentric rings of 6 points, and so 18 altogether, and the Lenstar uses 2 concentric rings of 16 points, giving 32 in total. It's important to note with the original IOL master, the problem with that was if you lost one of the dots, perhaps because the patient blinked, then you were throwing away an awful lot of the data it was relying on, and it was then having to do a lot of interpolation, which it's having to do anyway because it has no idea what's happening to the cornea between those dots. So really the more information you have, the more accurate your keratometry is going to be up to the point. So I'm going to compare that now with corneal topography. This is an imaging technique for mapping the surface of the cornea. Of course, the key advantage of some corneal topographers is that they will also give you a measurement of the posterior cornea, and that can be useful, particularly in some circumstances, which I'll come on to later. So let's just see what is topography. So topography, as you probably remember from your O-level or GCSE geography, you can do a topographic map of this hill in Germany. So you measure the height above sea level at certain points, you then connect all the points of the same height to make a contour line. So you might just about be able to make an out that down in the bottom left hand corner there's a contour line of 500 meters. So that 500 meter marks the 500 meter line all the way around that hill, together with its hills and valleys. So you then produce a contour map, and this is really what we're interested in when we're measuring the cornea, is to get a graphical representation of the shape of the cornea. Rather than height above sea level, of course, what we're doing is mapping corneal power. Now, the key advantage over keratometry is that you get a much larger area assessed. In a dedicated corneal topographer, you can often measure pretty much right out to the limbus, whereas the keratometry, just to repeat, really only measures the central 3 millimeters. You have no idea what's going on over that, outside that area. So how do these instruments work? Well, you've got different techniques. The pentacam takes a cross-section of the cornea. And what it does is take 25 of these shine fluid images, 7 degrees apart, right the way around the clock. They're photographed, and that image is then analysed to give a corneal curvature in each of those points across the cornea. The orb scan and an OCT works in a similar way. An alternative to that, and one which was around for a long time now, is what we call a pseudo disc, and this one's been around for well over 100 years. In the pseudo disc, you have concentric rings focused onto the cornea. The reflection of those rings is then photographed, and the separation of the rings is analysed by a computer. So the top picture there, you can see the T-cone, which is the corneal topography fitment that goes onto the Lenstar. And the bottom one is the image that projects, and it's very effective. So when we look at the separation analysis, where you've got a wider spacing, that means you've got a flatter curve, and a flatter curve, of course, means a lower refractive power in that area. Where the circles are closer together, you've got narrow spacing, that means a steeper curve with a higher refractive power. You can then convert all that data into a topographic map. This is where it starts to get slightly confusing. So we've got there a representation of the cornea. On the left, you've got a 3D representation, and on the right, there's a 2D representation. And they're color coded. So the steeper areas are warmer colors, and that means they have higher power. If they're flatter, they're colder and have lower power. So this cornea has had corneal refractive surgery, myopic, so it's flatter in the centre, then you get an area around the edge of the ablation zone which is steeper, and then it flattens off again. You have to be slightly careful with colour coding, because sometimes they are normalised to an average cornea, sometimes they are normalised to the steepest and flattest curves, so you have to be a little bit careful with the colour diagrams. It gets even more confusing than that, because there are two ways of representing those corneal topography maps. The first one, and the most commonly used one, is called the axial or sagittal power map. The reason this one is commonly used is that the central 3 millimeters gives you a very close representation of what you would find with keratometry, and also tends to reflect what you'd find on a refraction. Its other advantage is the maps are quite easy to interpret because they are smoothed out, which means you don't get much noise. But the problem with that is you're actually throwing away a certain amount of data, and peripheral data, particularly on the cornea, is not accurate. Now, the reason it's called an axial power map is that all the radii of curvature on that cornea are assumed to have a central curvature lying on the optical axis. So if we look at R1, that probably is a true central curvature, but R2 clearly has a much smaller radius. In fact, that is shown on the diagram. So that corneal bump appears to be flatter than it really is. So the alternative to that is what we call a tangential or instantaneous map, and by instantaneous I don't mean just in the click of a finger. What it means by instantaneous is instant by instant or point by point. So the tangential map is much more sensitive to local curvature changes. You get much better definition of peripheral points. But the key point is that all the points are independently calculated. Now that does make the map rather noisy, but it does give you some true radii of curvature. So we now see that R1 has remained unchanged with a genuine centre on the optical axis, but R2 now has its true radius of curvature, which is much smaller than we saw on the previous map. So it is, if you like, much more accurate, but it also makes it much more noisy and sometimes a bit more difficult to see what's going on. Here's two representations of the same cornea. This is the one that we saw earlier in the 3D map. So on the left we have the axial sagittal map, and you can see there that it's quite a smooth surface, not very much noise in it, but it does tend to rather underplay the local variations. On the other hand, on the right hand side we've got the tangential or instantaneous map. You can see there's a lot more noise in it, but also a lot more detail as well. So when you're looking at a corneal topography map, you just have to be aware whether you're looking at the axial or tangential map, because they will show different representations of the same cornea. I mentioned earlier that the Lenstar has a T-cone option, and the T-cone is a small corneal topographer. It covers central 6 millimeters, so again it's not the same as a dedicated corneal topographer, but in fact I've found that any patients who I identified on a full-on corneal topographer will also show as having, let's say, keratoconus on the T-cone. So I think that central 6 millimeter coverage actually does the job in terms of identifying corneas that you would want to know about as part of cataract surgery. So in that respect, it's a very good screening tool. So that Lenstar toric platform, together with the T-cone, it allows you to validate your keratometry. Warren Hill, the well-known Warren Hill, places his axis according to the steep meridian captured on keratometry, but he uses the corneal, I've lost my thread now. Sorry, he uses keratometry to work out, that's my age. He uses keratometry to work out the amount of astigmatism. But the point is that it reduces the need for multiple investigations, so you can very quickly screen cornea for disease to say whether the astigmatism is regular or irregular, and you also get the representation of the axial, tangential, also elevation data. Elevation data tells you how the cornea compares with a theoretical spherical cornea. So, do you need that? I think you do. We've had two cases recently where patients, if they've not had the T-cone, wouldn't have been identified as having keratoconus. So here's the first patient, which was a while ago. There's nothing really remarkable about that one. Cornea is a bit on the thin side, but not so far outside the standard range that you'd be getting excited about it. Cornea, not particularly steep, average cornea around 43 diopters, so nothing exciting there, and nor have they got particularly high amount of astigmatism. So what we say at our hospital is that if you've got more than 2.5 diopters of astigmatism on the cornea, then you will get a corneal topography. But that broad screening tool doesn't catch everybody. Fortunately on this one, we had already picked up using retinoscopy that the patient didn't have a normal corneal reflex. So we put them on the T-cone, and it's immediately apparent that this patient, it's the same patient we saw just now, has indeed got either keratoconus or pellucid marginal degeneration. So this patient would not be a terribly good candidate for toric, so you might get away with it. You certainly wouldn't want to put a multifocal lens in somebody like this. I said earlier that some corneal topographers will measure posterior corneal astigmatism, and this is now increasingly important because we're doing much more torics and patients have much higher expectations. So we know that the cornea is a horizontal oval, and 90% of eyes have a posterior cornea steeper vertically than horizontally. Now, in fact, we knew about this for 100 years ago or so with Yaval's rule, which says that the average patient has a posterior corneal astigmatism of about half a diopter, axis 180. But we sort of forgot about it, and for many years we did our toric calculations very happily, just ignoring posterior corneal astigmatism. And Doug Koch and his group in the States highlighted this for us just a few years ago, and immediately we got a big improvement in our toric outcomes. So I'm just going to spend a moment going through posterior corneal astigmatism, because it does seem to cause an awful lot of confusion. So to get your head around posterior corneal astigmatism, you can think of it that 90% of patients have an inbuilt correction of plus 0.2 diopter sphere, minus 0.4 diopter sill, axis 180. And what that means is when you're doing your toric calculations or considering whether a patient's likely to need a toric, if you ignore your surgically induced astigmatism, if you've got with the rule astigmatism preoperatively, so the keratometry is steep vertically, then the posterior corneal astigmatism will subtract from the corneal astigmatism in the final result. So if the patient starts off with a 1 diopter sill, you would expect that to come down following their cataract surgery. However, if the patient has against the rule astigmatism, which of course is more common in the elderly, so the Ks are steep horizontally, then that posterior corneal astigmatism will add to the corneal astigmatism in the post-op refraction, and therefore you'll have a lower threshold for corneal astigmatism in patients who are against the rule than you will for patients who are with the rule. So in the hospital, as I said, if we expect the patient to have 2 diopters or more of post-op astigmatism, then they will be offered a toric lens. So if you have somebody with a 250 sill, which is with the rule, then they may actually not get a toric lens, whereas somebody with a 250 sill who is against the rule will, because their astigmatism will be expected to go up. The Zeiss IOL Master 700 has another trick up its sleeve, which Zeiss called total keratometry. So the way this one works is that you've got your standard keratometry on the front surface of the eye, so 3-zone keratometry. That then allows you to produce a toric model. It also does a swept source OCT scan of the cornea. So broadly what it does is to add the corneal thickness of those points to the toric model, and that allows you then to model the posterior cornea. It then goes through an algorithm to give you a toric fit, applying some fudge factors, and then you will get a measured posterior corneal astigmatism. And of course it's not going to be exact, because the back surface of the cornea, your estimation of that will only be as good as your estimation of the front surface of the cornea. So if your front surface is varying a lot during the measurements, because of a dry eye, then you won't get a reliable posterior corneal astigmatism measurement either. So it has some merit, but it's not perfect. So that really brings me to the question of, do we need to measure posterior corneal astigmatism at all? So the Baylor study, which was Doug Koch and his team in the States, measured the posterior corneal astigmatism as a proportion of total corneal astigmatism, and published in about 2012. Did a lot of patients, and they found, Yavel's rule actually does hold true. So you can see there that patients tend to switch from being with the rule to against the rule with age, but also that the posterior corneal astigmatism actually stays fairly constant throughout life. And indeed 90% of patients fit that model. So if you start to measure the posterior corneal astigmatism rather than working on a nomogram, say, then you might pick up a percentage of the 10% who don't fit Yavel's rule. So the gains tend to be fairly minimal, you would expect, and that indeed was confirmed by Graham Barrett at the ESCRS conference back in, I think it was 2015 now. So he found that even with his own formula, there was little or no benefit for non-refractive surgery patients, and in fact they did slightly worse for patients who weren't having a toric lens. With the toric lens, then you did gain a little bit. So there's his comparison, and as you can see, although there does appear to be a difference, almost certainly it's not statistically significant. Where you do gain by using Barrett TrueK TK is where you've got patients who've had refractive surgery. And there you really do gain, because one of the problems with refractive surgery patients, as you'll hear later in the talk, is that it's not uncommon to get a certain amount of ectasia, where you've got steepening of the front of the front of the cornea and the back surface of the cornea. and you've broken down that relationship between the two. So using the TK, or in fact any topographer which will measure the posterior surface, you will do significantly better using that true K TK formula rather than just the standard true K formula. So you can see there you've got to around getting about an extra 8 to 10% within your target range. So certainly well worthwhile. As I say, you can actually do this on his online calculator using any measured posterior corneal curvature such as the pentacam. So unfortunately it was called true K TK because I think the TK bit does get rather confused when it appears twice in the same name. So surgically induced astigmatism, this again is something which causes quite a bit of confusion. So surgically induced astigmatism happens because the way the cornea is built up is a series of fibres that cross the whole width of the cornea from one side to the other. And when you make an incision in one of those fibres, it flattens the cornea in that meridian. I explain this to patients in terms of a circus big top. So I say, if you imagine a circus big top, a round big top that's supported by guy ropes, if you were to cut one of those guy ropes, then the tent is going to sag in that area and it will change shape. So that's the analogy I use when explaining to patients how their cornea changes, and in particular when they've changed in an unpredictable way. Now the effect depends on a number of factors. It depends on the size of the incision, as you might imagine. If you make a bigger incision, you're cutting more of the guy ropes, and therefore you'll get more of an effect on the cornea. And back in the day when I started in optometry, and they were still doing extracapsular cataract extraction, and it was not unusual to see, we had one particular surgeon where it's not unusual to see a tensil following the surgery. Happily it went down once the stitches were removed. But the point stands that it's not unusual to see quite big sills in patients who had cataract surgery back in those days, and that was simply down to the size of the incision, which was way bigger than the 2mm or sub 2mm incisions that are used now. The way the wound is constructed is also important. It also makes a difference whether you make your incision into clear cornea or right at the limbus, or indeed do a scleral tunnel. And there's no question that the more central you make your incision, the bigger the change because it's close to the centre. And that takes us on to the last point, which is it does make a difference whether you tend to do your incisions superiorly or temporally. That's because the cornea is a horizontal oval, so if you're doing a temporal incision, you will have less surgically induced astigmatism simply because it's further away from the centre. There's been quite a long-running argument in ophthalmology as to which is best, superior, temporal, or on the steep axis. And a few years ago, when ESCRS was run in London, Haag-Streit hosted a lunchtime talk with Graham Barrett and Warren Hill, both equally eminent surgeons. Graham Barrett says always do temporal incisions. He said you'll get less surgically induced astigmatism. He said predictably it's about 0.12 of a diopter in his hands, as it is for most surgeons who operate temporally. Warren Hill, on the other hand, always operates on the steep axis, but being quite meticulous in his preparation, he knows exactly what his average surgically induced astigmatism is right the way around the clock, so he's able to take that into account in his calculations. There are other things to take into account, of course, because there's always been this traditional view that temporal incisions are a bit more prone to endophthalmitis, but it's an ongoing debate. And it's one that doesn't really have a right answer. So, how do we take surgically induced astigmatism into account? Well, we do it with vector maths. So a vector has a length which is equal to the cylinder power, and of course an angle which is equivalent to the axis. And what that vector maths allows us to do is to resolve all the different vectors. So if we start off with corneal astigmatism, which has size and direction, we add to that superior a superior incision of SIA, represented by the white arrow. We're then going to put a toric lens in with angle as shown and amount of toricity as shown. But the problem is that it doesn't quite get back to the origin. So the result is you've got some residual astigmatism. Now, by manipulating the surgically induced astigmatism, we can actually reduce that residual sill. So here's our original corneal sill. We're now going to change the position of our SIA. So we're going to make the incision at 140 degrees instead. So the angle of that has changed. We then put another toric lens in, and that toric lens takes us back to the origin. So we now have 0 residual astigmatism, assuming everything comes out as predicted. So by altering the position of your incision, you can actually reduce the residual sill to a very small value. So in summary, accurate corneal measurement is essential, but as I said earlier, it is really becoming one of the limiting factors, largely because of the tear film. Warren Hill uses keratometry for the amount of astigmatism, and topography for setting the axis of his calculation, but also for screening out irregular astigmatism. It's absolutely vital now to incorporate posterior corneal astigmatism, and all the online calculators will do that. So Alcon, for example, changed theirs probably 2, maybe 3 years ago. Prior to that, it didn't incorporate posterior corneal astigmatism. With Zeiss, you can switch the algorithm on and off, so you can choose not to have it calculated. Why you would, I've no idea. And so it doesn't make a huge difference whether you measure that posterior corneal astigmatism or just assume that the patient is probably going to fit that 90% model. Of course, most of them do. But also you can use the toric planner, which is built into the Lenstar, to adjust the position of your surgically induced, of your incision, and therefore the surgically induced astigmatism, and you've got that superior versus temporal versus on-axis debate as discussed. So that's the first part of tonight's talk on toric lenses. So I'm now going to move on to talk a bit about biometry post-laser refractive surgery. And this is one question which we can guarantee comes up every time during our improving outcomes in biometry courses. So the problem is it's a bit of a time bomb. There have been well over 40 million refractive surgery procedures worldwide since 1990. And you'll remember that back in those early days that there was a huge rush to get this done. There were lots of patients who had this sort of pent-up demand, who were very keen to have their refractive surgery procedures. So there were a huge number carried out in the 90s, but then the centres closed down because they were no longer seeing enough patients. The equipment was moving on so quickly they couldn't afford to keep investing in new equipment every couple of years, but you had to keep up with the technology. So those centres closed down, and in many cases the records are lost. But it's worse than that because patients' recollection is poor. The one thing you have to know to do these calculations in post-refractive surgery patients is you have to know whether the patient was previously myopic or hypermetropic. And without that information, you cannot make even a good stab at the calculations. And patients' recollection is very poor. You can say to them, well, could you see to read without your glasses on? Some of them just can't remember at all. And you then have to do corneal topography, try and get an idea from the cornea. You can measure axial length and see whether they're likely to have been myopic or not, but it's all a little bit of guesswork. Occasionally patients will turn up with 100 pages of their records, when in fact all the detail I want is just on page number 37, and I've got to wade through the whole lot to try and find the data I want. But of course these are difficult because these patients have paid a lot of money to be ametropic. And of course nowadays the refractive surgery is extremely accurate, and the majority of patients are extremely satisfied with the results. And of course when they come on to have cataract surgery, they have those same high expectations. And the problem is it's really hard to meet those expectations because it is still very unpredictable. I think it always will be. So what's the problem? Why is this such a big deal? Well, the first problem is corneal power. So I said earlier, the keratometrists measure the central 3 millimeters. Of course, ablation zones typically now are 7 millimeters or more. And the corneal, the keratometer has no idea what's happening outside that central 3 millimeters. We then have to use the corneal index to calculate the power. As I said earlier, what you're actually measuring is the curvature, and you're then converting it to the power. That corneal index that we talked about earlier treats the cornea as if it were a single surface, which of course it isn't. And the problem with that is that the corneal index relies on a standard relationship between the front and rear surface. So if you're doing a myopic refractive surgery, then you'll flatten the front surface. As I said earlier, you're thinning the cornea, weakening it, so ectasia is not uncommon. But the upshot of that is that corneal power will tend to be overestimated in myopes, and it's even worse with higher corrections. And because the corneal power is overestimated, you will end up putting in a weak IOL than the patient really needs, and therefore they end up hypermetropic. And patients who started life as myopes, then got to zero, will not appreciate being made hypermetropic. So the second problem is the anterior chamber depth. So, as I said earlier, we only measure corneal topography keratometry in the central 3 millimeters. The problem is the formula doesn't know that. It assumes that we've got the same curvature right across the entire width. So here's our virgin eye, and we're now going to flatten the front surface with a laser and create a new radius curvature. Here's our true anterior chamber depth. The problem is the formula thinks the eye looks something like this. Now, of course, this is exaggerated for the purpose of the diagram, but you get the picture that the Kroll formula now thinks the anterior chamber depth is much shallower than it is. So the IOL thinks the IOL is sitting close to the cornea, and again, with a previously myopic eye, you'll get a calculated IOL power which is too weak. Over the years, there have been over 30 suggested solutions. There was clinical history methods, which use the patient's refractive error, but of course you have myopic shift in a lot of cataract patients, ectasia as mentioned. You could use the pentacam to measure the cornea. That was tried, but it didn't correct the problem with the anterior chamber depth and the effective lens position. There was also the contact lens method, which some people had success with, but is now discredited. But certainly in those early days, there was an awful lot of guesswork involved. I remember one patient who we still see now in the glaucoma clinic many years later, did the calculations, hoped for the best, and he came out +2. So okay, that's not great. So we adjusted the calculation for his second eye. We did the second eye, that came out +2 as well. So he ended up having piggybacks in both eyes. So it just shows how dreadfully unpredictable these eyes can be. But we're much better off now, and I think the man who really cracked it for me was this chap, J. Berry, in 2003. And what he did was to introduce the double K method. And the reason it's called the double K method is he used 2 different keratometry values in the calculation. So the corneal power, you will measure the corneal curvature to get a reasonable estimate of corneal power. When it comes to calculating the anterior chamber depth and therefore the effective lens position, you're going to use either the pre-LASIK keratometry if you've got it, or even if you just use an average value of 43.5 diopters, then you'll get much better results. So say it's using two different values of keratometry in the calculation, and that really was a massive step forward and really got a big leap in our results. And I think J. Berry perhaps doesn't get the recognition that he deserves, but that double K method is used in pretty much all the modern calculations for post-refractive surgery. So of those 30 those 30 methods that were used over time, there are probably about 10 which are regarded as being best and put in terms of being least unreliable. Which is the best of the best? Some of them need prior data, some don't. And then again, when you're trying to compare them, what data you're going to look at? You can look at the mean error and standard deviation to get an idea of spread. You could look at the range for the sort of worst patients that you've got, or percentage within half diopter. So there are different parameters that you need to look at to judge these different formulas' performance. But happily, it's got slightly better, slightly easier recently. So there were 2 key papers in the last few years for myopes, and this one really was looking at the True K formula compared with different different methods that are available on the ASCRS website. So this was a group led by Adi Abulafia, Warren Hill, Doug Koch, Lee Wang, and Graham Barrett. So some really big names in biometry and cataract surgery. So you could rely on that. And then a couple of years later, another paper from Savini and Hoffer. Again, Hoffer, Ken Hoffer with his Hoffer Q formula. Again, very big names who did a similar study. So let's just have a brief look at those results. So the Abulafia and Hill paper, we've got box and whiskers plots. So broadly, the smaller the box and the shorter the whiskers, the better the formula. But if you but rather than just looking at the box and whiskers, you also need to look at the outliers. So you can see there that some of the formulas come out with some pretty dreadful outliers. So you've got some where the patients come out +3 instead of 0. Those patients are going to be desperately unhappy. So what you want is small box and whiskers, but also not many outliers as well. So traditionally, it's been suggested you could look at the 10 best formulas, let's say, find an average of them, and then use that. So that's on the right-hand side of the slide. That's for the average of those 10 best formulas. But you can see you've still got some outliers, reasonable box and whiskers. But the one next to that is the Barrett True K formula, and that actually outperforms or performs equally as well as averaging all those 10. So the Barrett True K formula has really become our go-to formula for post-refractive surgery patients. Happily, that was backed up by the Savini and Hoffer paper, which was really a review paper rather than original data, and they came up with the same conclusion that Barrett True K was consistently good. The Savini calculation was also good, but the numbers were relatively small, and again, has not really gained much penetration. Masket, which was previously thought to be quite good, turned out to be rather variable in this particular study. So that's if you've got historical data. If you haven't got historical data, then the formulas behave rather differently. So for many years, the go-to formula was the Haag-Streit formula from my old friend, the late Wolfgang Haigis. And Haag-Streit was very good. Again, we got some excellent results. I remember our first 3 patients who did with Haag-Streit all came out pretty much 0. And we thought, great, we've cracked it. Next patient, +2. So we hadn't cracked it at all. We just got lucky with those first 3. But again, Savini and Hoffer showed that Barrett True K, no history version, was consistently good. Shamus, again, thought to be quite good previously, turned out not to be so good. And Haag-Streit, well, was a bit all over the place, really, but it was good in its day. So that's myopes. But for hyperopes, things were a little bit different. There was another paper published in 2017 where they compared using Holiday 1 Hoffer Q with the Masket formula, compared that with Barrett True K, Shamus and Haag-Streit, and really found no significant difference between those 3 formulas. So the take-home message for that one is that you can use Barrett True K for hypermetropic patients as well as for myopic ones. And again, it was that was valid for Barrett True K or Barrett True K TK, as discussed earlier. So lots of these formulas built into the Lenstar. If you don't have a Lenstar, you do have access to the ASCRS website. This has been around for a long time now, and it does get regularly updated as new formulas come into fruition. But also what they do is to take off some of the less reliable formulas as time goes on. So what you do is to enter as much data as you've got. So there's some basic data which you have to have, which is keratometry and the patient's axial length, as you might expect, and anterior chamber depth. Broadly, the more information you can put into it, the more formulas come into play. Once you've filled as many boxes as you can, and I should mention at this point, I would recommend that you fill in the lens constants that you want to use. It will calculate lens constant equivalents for you, but I've never been terribly convinced by the numbers that come out. So I would encourage you to have a look at your standard biometry constants and plug those into the formula, and you'll get better results. You then hit calculate at the bottom there, and this is the results screen from 2015. So they've taken out all the clinical history methods because they were shown to be really lagging behind all the others. So on the left-hand side, you've got formulas that will use the prior data if you have it. If you don't have the prior data, then the formulas on the right-hand side will still give you a result. And you can either look at the average power given for all those formulas. You can look at the minimum, the maximum. Which one do you go for? We started off doing this, and we used to find an average, but then I looked back at our data and I realised that the Barrett True K was really giving us what we predicted. It was really making the best prediction of what actually happened. So after a while we dropped the average bit and we just resorted to using Barrett True K, and happily, because that's built into the Lenstar, we didn't have to transfer the data with all the attendant risks of typing in a wrong figure. So I think one of the most important things in the cataract clinic is you've got to ask the right questions. So of course we always say to patients, have you had any previous eye surgery? Have you had any previous eye problems? And they'll say no. In fact, they've had refractive surgery, but they don't think of it as surgery. Nobody came at them with a scalpel. They certainly didn't think it was an eye problem because they came out and they could see brilliantly, no problem. So you've got to get that word laser in there somewhere, and it has been suggested if you don't ask the patient routinely when they've had laser eye surgery and it turns out they did, that you could be accused of negligence. It's also important if you use, if they do the keratometry, if they do lens calculations rather, using the standard formula, don't print out the results because they will find their way into the notes. But also you've got to advise the patient that the results are unpredictable. You're not doing yourself any favours if you overplay it. So I tend to quote the patients the figures that if we've got previous history, and they've got about a 70% chance of not needing glasses for distance, but of course that means they've got a 30% chance that they will need further correction. And if we've got no history, that drops to about 60%. So that finishes my talk. There is another talk coming up quite soon from Warren Hill, the brilliant Warren Hill, with his latest version of the Hill RBF formula, and I'd highly recommend that. I think Grant's going to talk a little bit about that now, and we're happy to take any questions.
David, thank you very much for that. At the moment, we have no questions showing on the Q&A tab. I have a question for you, David. You've been speaking now about post-refractive patients, certainly on the courses that I've been involved with for 4 or 5 years, and previous to that as well. Are we seeing any improvement in the outcomes for these patients? Is there evidence that that they're getting closer to target outcomes as we move forward?
Yeah, it's a good question, and I think there's no question. So from time to time, the college does carry out a major review of cataract outcomes, and the last one really was quite poor. So we were only seeing around, I think it was 60% of patients were getting within half diopter. So really quite poor figures when you think that the best people around the world are getting well over 90%. So the NHS was not doing great. I think we are slowly chipping away. Certainly the 1 or 2 hospitals where I've carried out biometry audits at their request, found some really examples of really poor practice around the country, but also some examples of very good practice too. Happily, a lot of those are people who've been on the improving outcomes course. So I think the biggest wins probably have been moving people on to firstly understanding the importance of biometry, so paying much more attention to it, but also moving people onto the multivariable formulas such as Haag-Streit, Barrett, and so on.
Is there any evidence that patients are being provided with their post-op refraction when they go for surgery and encouraged to keep that information, make it available should they require cataract?
I do ask occasionally, and I think surgeons now are much better at providing that information because they now understand it. To be fair, back in the 90s, I don't think we realised quite what a time bomb we were storing up for ourselves by not giving the patient. So it's things have moved on, and I think they are now much better at saying, patient, you must keep this data. Take a photograph of it and store it on your computer. Generally, the data is available. There are some patients who can't even remember where they had the surgery, let alone any detail about it. But the ones that can, often that data is available, particularly for the bigger centres, although they do tend to charge for it, usually around sort of £40–50.
A couple of questions now. Would you be confident enough in Barrett True K's to use a multifocal IOL lens in a previous LASIK patient?
I think that would be a very brave surgeon. Two reasons. One is that even the best Barrett True K TK is still only going to get up to around 70–80%, and that's not really good enough for multifocal lenses. The other problem with multifocal lenses is that you are introducing further aberrations into a cornea which already has aberrations. So with a patient who's had LASIK, as you'll know, a lot of them complain about halos at night. The reason for that is, of course, their cornea is not a single power. It's got multiple powers, and therefore you get multiple images on the back of the eye. And you get those same effects, of course, with a multifocal lens. So you are adding one set of problems onto another set of problems, and you're really asking for an unhappy patient. So we do a lot of multifocals, and the one patient we've had who was desperately unhappy with them was a patient who had talked us into multifocals despite having had previous LASIK. He got quite a good refractive outcome, but was just never happy with his vision. I suspect because he had really poor contrast sensitivity. So personally, I wouldn't. I'm sure there are people around the world who are brave enough, but I wouldn't do it.
Okay, another question. For using the ASCRS online calculator, keratometry is required. If we do not use Lenstar, which has already had formula application, would you use K values for a corneal topographer?
I think it's more important to be consistent. So you can take values off your corneal topographer, particularly if it's one of the ones that are actually listed in the SCRS website. But certainly Wolfgang Haigis with the Haigis L formula said you must use keratometry values from the IOL master, because that's what I used when we were putting the formula together. So I wouldn't advise mixing data. If it says keratometry, it means keratometry. If you've got a corneal topographer and it's one of the listed ones, then you can put that topography result in, but I wouldn't mix the data. That's really asking for problems. There are a couple of questions at the top there asking what if the patient has no data, what would you do for laser? And the answer is to use, again, I would go back to Graham Barrett's True K formula. So there are two versions of it, one where you've got prior data, and one where you haven't got prior data, and it will automatically switch into whichever one you fill in the data for. So if you didn't have any prior data, it's not a huge problem, but the percentage of accuracy will drop about 10%, so down to about 60% compared with 70%.
Excellent. We have somebody else asking in the chat about how long biometry measurements are valid for. How long would you trust them for? And would you then trust the old axial length measurement with new keratometry?
Yeah, it's a good question, and it's one which was only answered fairly recently. So we used to set a 1 year rule, but it was just a finger in the air. That we had no real evidence that the readings change. It just seemed like a fairly easy rule to follow. But Paul Ursel and his colleagues did quite a good study on about 300 eyes, I think, where they looked to see how long those readings were valid for, and they found very little difference up to 3 years. So we've put a 2 year limit on ours. So what we actually say is the biometry must be done within 2 years of listing. So we use the date of listing rather than date of surgery, because of course when you list the patient, you don't necessarily know when the surgery is going to take place, particularly at the moment. So we say it's got to be within 2 years of listing. So that gives us sort of 1 year leeway. But it's actually nice to have some published data and to be able to extend our 1 year limit a little bit, and actually with some data to back it up. So yeah, I would say if you use 2 years from the date of listing, then that's probably perfectly defensible.
Thank you. There's another question, David, there. I don't know if you can see it, about using the T-cone. Yeah,
it's a slightly personal preference. So Peter Wilson, who also teaches on the Improving Outcomes course, their T-cone never comes off. They use T-cone on all their patients. I tried that, and certainly I was okay with it, but some of the staff found it a bit fiddly. It is, of course, much more fussy in a way because you are collecting more data, and therefore you've got to have a more stable tear film. So I think for an experienced user, yeah, you can leave the T-cone on. In our clinics, if I'm doing it, then yes, I can use the T-cone. If the nurses are doing biometry, then we tend to take the T-cone off and they put it on or send the patient across the corridor for full-on corneal topography with the pentacam if we find more than 2.5 diopters of corneal astigmatism. That's really just to screen out patients with corneal ectasia.
Excellent, thank you, David. I can see no other questions popping up now. If you do have questions that we didn't get to or you haven't been able to ask, please send them to me via the email address you'll receive in tomorrow's email. In that, I'll also include a link to our interactive biometry learning modules, which will be available without a user account until February of next year. I'll also include a link to the Hill RBF3 webinar that David mentioned a moment ago. This has been organised by Haag-Streit USA. Excuse me, it's on the 7th of January next year. Features Dr. Warren Hill himself explaining the artificial intelligence behind Hill RBF3 and how it will result in up to 50% less out-of-bound warnings. There is a slight caveat with that webinar. As I say, I'll send you the link to join that tomorrow, but it will be at midnight UK time, so 11:59 on the evening of the 7th of January. I think if you register, however, you will then be sent a link to a recording of the webinar, so it's probably worth registering even if you've no intention to stay up quite that late to join it.
Grant, I just realised, oh, sorry, I just realised I didn't answer the second part of that last question from Karen Robinson. So if you've got a patient with biometry outside the States who now needs an A scan, which is then difficult or variable, would you trust the old axial length for the new case? What I would say is that in most hands, if you have to do an A scan, I would say that an A scan done today is likely to be less accurate than an optical biometry done even 2 or 3 years ago. So our rule is that if you get a patient who comes back for second eye surgery 3-4 years down the line, their other cataract has got so bad you can't now get an optical scan, rather than doing an A scan, we would use the old optical biometry. Even though it's a little bit out of date, it's likely to be more reliable. And the chances are the keratometry values are not going to change significantly over that time, bearing in mind the fairly poor repeatability of keratometry readings on a test-retest basis.
Thank you, David. We're approaching 7:30, so I think we'll bring proceedings to a close. I just want to finish by saying we're currently planning a number of new webinars for 2021, as well as the reintroduction of live face-to-face training events. Tomorrow's email will provide a link for you to join our Haag-Streit Academy mailing list to ensure you're kept informed about all our educational activity in the new year. I'd just like to thank David once again for both last week's webinar and for this evening. It's always a pleasure listening to David speak. I'd like to thank Sam as well for assisting me in the background. And then I'd like to thank you all very much for your time this evening. Enjoy the festivities over the next couple of weeks, however limited they may be, and have a safe and happy new year. Good evening and thank you very much.